In this lecture, we'll introduce the normal probability distribution. This is probably the most well-known continuous probability distribution, and it's one of the most important because it provides the foundation for almost everything we're going to do for statistical inference. So we want to be sure that we understand a little bit about the normal distribution and its properties and how to compute probabilities using this distribution. The normal distribution is the distribution that gives rise to this very common bell-shaped symmetric curve that you see to the right-hand side of the screen. Most people have seen a curve that looks like that, at least on the front of a statistics book, if not in other places. And the function that gives rise to that curve is seen in the upper left-hand side of the screen. The interesting thing about that function is that it's completely defined by its mean and standard deviation. In the formula, mu is equal to the mean, and mu describes the center of the distribution, or the point where that peak takes place. Sigma is the standard deviation, and that describes the spread of the distribution. So larger values for sigma will give a distribution that is more spread out with wider tails. Smaller values of sigma will give a distribution that's more tightly clustered around the mean. The standard normal distribution is a special case of the normal probability distribution where the mean is equal to 0 and the standard deviation is equal to 1. This is an important distribution historically for a couple of reasons. First, if you have any normal random variable with a mean of mu and a standard deviation of sigma, no matter what those values are, if we take that random variable, we subtract its mean and divide by its standard deviation, that gives rise to a new random variable we typically refer to as z that has a standard normal distribution. That process of subtracting the mean and dividing by the standard deviation is called standardizing the normal random variable, and that z value is typically referred to as a z-score. This was important in the early days of statistical analysis because it's very difficult to actually compute integrals based on the normal probability density function. And so in the early days, there would be rooms full of women who had these adding machines, and their job was to tabulate probabilities for the normal distribution as well as other probabilities. And in order to simplify things, they would typically tabulate these probabilities and they would put them into a table that they could share with practitioners so the practitioners could compute the probabilities on their own. The challenge with the normal distribution is that it's possible to take on any value for mu and any value for sigma. So there's an infinite number of possibilities of combinations of means and standard deviations for a normal distribution. In order to simplify this process, rather than having hundreds of thousands of tables, the computations were done for a standard normal distribution, the tables were produced, and the practitioners could take their problem with their own mean and standard deviation, they could standardize that random variable, and they could use the standard normal table to actually compute probabilities. It turns out that we've done that even up into recent years, and the tables that we have now are still based on standard normal probabilities. So this is a standard normal table. It's the table that you'll see in this class. A couple of things to notice here. First of all, as I said, it's for the standard normal distribution. So this table is assuming probabilities based on a mean of 0 and a standard deviation of 1. And the other thing just to be aware of is that in this particular version of the table, we're computing less than probabilities. So this table is giving us the probability that z is less than or equal to some value little z. So we need to understand how to use this table to actually compute probabilities. We're going to look at a couple of examples. We're going to look at a less than example, a greater than example, and a situation where we want to know the probability that z is between two values. The first example that we'll look at is the simplest because the table actually gives us the less than or equal to probabilities directly. So to find the probability that z is less than or equal to some value, we need to be able to look up that z-score and then come out with a probability. To look up the z-score, we'll start by finding the first two digits of our z-score in this column. So z equals 1.2. There's the value for 1.2. And then we're going to find that third digit across the top, across these rows. So 0.03, that gives us the third digit, 1.23, and the probability is right there in the table, 0.8907. So the probabilities in the table, those are just less than or equal to probabilities, and it's simple enough to find those probabilities by just looking up that z-score. So the first two digits are found in that leftmost column, the third digit is found in the topmost row, and the place where they intersect in the table gives us the probability. Now, suppose that we want to find the probability that z is greater than or equal to some value. Well, in this case, if we shade the probability that we're interested in, this is the probability that we want, the probability that z is greater than or equal to 0.54, but we're not given that probability in the table. What we're given is the less than probabilities. So we could find the probability that z is less than or equal to 0.54 in the table. We know how to do that. We just found that out. But we don't want that probability. What we want is the opposite of that. So if we apply the law of complements and recognize that the area under the curve is equal to 1, the probability that z is greater than or equal to some value is just 1 minus the probability that z is less than or equal to that value. And we know how to compute that probability from the table. We'll look up 0.54, and we find that the probability from the table is 0.7054. So if we plug that probability into our equation, 1 minus 0.7054 is 0.2946, and that gives us the probability that we need. The third possibility when dealing with normal probabilities is the probability that z is between two values. And so again, you see here what we're interested in. The shaded probability is the probability that we want to find, but obviously we don't have between probabilities in our table, so we need to rewrite this probability in some logical way such that we can only look up less than probabilities. Well, it turns out that we could find, for example, the probability that z is less than or equal to 0.27. That would be everything to the left of 0.27. But that would be a little bit too much because that includes this unshaded part to the left here, and we don't need that part. So we would need to sort of subtract that bit out. Well, it turns out that unshaded part is just the probability that z is less than or equal to negative 0.78. So if we compute the probability that z is less than or equal to 0.27, that gives us everything to the left. If we subtract off the probability that z is less than or equal to negative 0.78, that gets rid of the unshaded part that we don't need, and we're left with what we're interested in the center. And so that's the way we're going to compute these probabilities. If you have a scenario where you need to compute the probability that z is between two values, you find the probability that z is less than or equal to the larger value, subtract off the probability that z is less than or equal to the smaller value. Those two probabilities you can get directly from the table. If we plug those in, then we can get the probability that we need, which is 0.3887. So we have three different scenarios that we'll need to be aware of when using the table. Even though the table gives us the probabilities, there's some manipulation that needs to take place before we can actually pull values out of the table in most cases. If we wanted to do these computations in Excel, there is a probability function in Excel called the norm.s.dist function, and that function essentially will give you the table values. When you plug in the z-score, then it's going to spit out essentially the probability that is given to you in the table. So hang on to that for just a minute and we'll come back to probabilities in Excel. But you can actually look these probabilities up in Excel rather than using the table if you prefer to use software. All of that's fine and good if we start with a standard normal random variable. But if we don't have a standard normal random variable, we have to add a step to our process. So we always want to write down our probability statement, sketch our curve. We want to shade the region of interest just to help orient ourselves to what we're trying to do. And then when we have a random variable that is not a standard normal, we're going to need to compute z-scores for those delimiting x values before we continue. Once we do that, we can use the standard normal table or the norm.s.dist function in Excel to obtain the probabilities. So let's look at an example where we have a mean and standard deviation that are not 0 and 1. Most people are familiar with IQ tests, and it turns out that IQs that are measured on this particular Binet-Simon intelligence test are normally distributed with a mean of 100, right, so not 0, and a standard deviation of 16. So the mean is 100, standard deviation is 16, and we want to know the probability that a randomly selected individual has an IQ of less than 115 or an IQ between 115 and 140. And another question that's a little bit different but also related to the normal distribution, we may want to compute percentiles for the distribution of IQs. So let's take a look at this first probability. We want to know the probability that our random variable x is less than 115, that IQ score is less than 115. Well, we know x is not a standard normal random variable, so we're going to need to take a little side trip to compute a z-score. So remember, z is just equal to x minus mu divided by sigma. In this case, x is 115. Our mean for the distribution was 100, and our standard deviation was 16. And if we do that math, it comes out to be 0.94. So we can now rewrite our probability in terms of a z-score. This is just equivalent to saying the probability that a standard normal random variable is less than 0.94. And we know how to do that computation. We can do that directly from our table. We just find 0.94 down here. Right, there's 0.9, and here is 0.04. And if we go into the table and look up that probability for 0.94, we see that the probability is 0.8264. So that's easy enough. We just had one extra step. We needed to compute that z-score. If we want to know the probability that an individual has an IQ between 115 and 140, again, we're going to need to take a little side trip and compute some z-scores. We've already done that for 115, so we don't have to do that again, but we don't know the z-score for 140. So if we do this math, 140 minus 100 divided by 16, that comes out to be 2.5. So now we need to rewrite our probability statement in terms of a z, in terms of a standard normal. From the previous problem, we know that the z-score for 115 is just 0.94. We just computed the z-score for 140, that's 2.5. Right, and so now we need to rewrite this probability statement in terms of less than or equal to probabilities. So remember, that's just the probability that it's less than or equal to 2.5 minus the probability that z is less than or equal to 0.94. If we go and look those values up in the table, 2.5, 0, right? So if we find that value in the table, that gives us 0.9938. From the previous example, we know that the probability for 0.94 is 0.8264. And we can do that subtraction. And if we do that subtraction, we get a probability of 0.1674. So again, the process is the same. We just have to take that little side trip to compute our z-scores. Now, a slightly different question, what's the 90th percentile for IQs? So if you think about it, we're sort of asking the reverse question in this situation. In this situation, we're saying that we want to find the value p, that percentile, such that the probability of being less than p is 90%, right? Just recalling the definition of a percentile. And so in order to do that, essentially what we need to do is we need to look up this probability and kind of back up and then figure out what would be the value of p. So if we go into our table, we want to find the value in the body of the table that is as close as possible to 0.9, and it turns out that if we do that, right down here at 0.8997, that's about as close as we can get to 0.9. Now we need to back out the z-score. So if we go out to our column, we see that we have 1.2, and if we go up to the top, we see that that third digit is 0.08, and so our z-score corresponding to this percentile is 1.28. But we're not quite done yet, because that z-score would actually be the value from a standard normal distribution, and our distribution has a mean of 100 and a standard deviation of 16. So if we do a little bit of algebra, we could figure out that an x would be equal to mu plus sigma times that z-score, right? If we just rearrange the formula for the z-score, we can see that our x value would actually be equal to the mean, which is 100, plus the standard deviation, which was 16, times that z-score, which was 1.28, and we come up with a value of 120.48. So the 90th percentile for IQs in this case is 120.48. So just another way of using these normal probabilities to help us get some information about our data. Now, we've had to do a lot of manipulation with these tables in order to take normal distributions and make them look like standard normal distributions. But it turns out that it's much more computationally simple now to compute directly the values for normal probabilities. And Excel has functions called the norm.dist function and the norm.inv function that will allow us to compute these cumulative probabilities directly for any normal distribution with any mean and any standard deviation. So it saves us just a little bit of work. We don't have to compute that z-score in order to find the probability. And for the norm.inv function that computes those percentiles for us, it gives us an exact percentile instead of having to interpolate or kind of use the closest possible value in that table. It allows us to put in the value of 0.9 exactly and find the exact x value that corresponds to a 90% probability. So this would be a good point to stop and watch the normal probability in Excel interactive tutorial, which will give you more detail on how to use these functions in Excel to compute normal probabilities, and it will give you the chance to practice on your own.